Hi, this is Team 1171 from University of Vermont, and the problem we are working on is it's raining space dust. So the goal of our project is to explore how cosmic dust particles found on the layer of Earth's surface can be used to understand the cosmic phenomena, the region the cosmic dust entered the Earth's surface, or the influx of them, and things like that. In this project, what we have tried to do is, first of all, try to predict and examine how the size of the cosmic dust particles or their velocity will basically determine if they survive or not, right? And how much the fraction of the cosmic dust particle will enter the Earth's surface and things like that. And then later on, we also discuss if it's possible to use an estimate of the distribution of particles of cosmic dust found within the layer of Earth's surface to basically backtrack the distribution of cosmic particles that actually entered the Earth's atmosphere. Yeah, so first of all, a brief intro to cosmic dust. These are tiny solid particles from the space, right, that enter Earth's atmosphere from variety of sources like asteroids or comets. And they're pretty small, like 100 micrometer in diameter, and even their mass is around 10 to the power minus 10 kilograms. And a recent study shows that around 15,000 tons of micrometeorite dust enter the atmosphere each year. But even then, very small quantity actually reaches the Earth's surface. It's mainly because they have really high speed, like 11 kilometers per second, and because of that, there's frictional heating, which often burns them or vaporizes them. And the studying of the cosmic dust particle is actually important because from their chemical composition, we can actually know about the chemical composition of asteroids or comets, right? And also the influx, their influx can actually help us predict some important cosmic phenomena like asteroid collision or something in the comets and things like that. So yeah, in our project, we will basically try to make a mathematical model to simulate what happens to this cosmic dust using aerodynamic drag and deceleration and thermal heating and ablation. The first one to actually track the velocity and second one to track whether the particle survives or not. So yeah, first of all, using the drag acceleration model, we first of all assume that the cosmic dust is a spherical particle and the drag force is the standard drag force per a spherical particle, half drag coefficient, atmospheric density, and then cross-sectional area velocity square. And from Newton's second law, the retardation will be force over m, right? And also there's gravity, that's pulling the object, the cosmic particle, and because of that, we have the given differential equation dv over dt is gravity minus the retardation due to drag force. During high speed, the drag force dominates over gravity, but gravity becomes relevant once the particle reaches terminal velocity. The next model is about thermal heating and ablation model. And here we look at how the velocity of the particle will actually hit itself and whether it will melt or not. So we basically have energy conservation equation. In the given equation, the left side is basically the net heat energy. In the first term over there is the heat received from particles kinetic energy due to drag. And the next term is the radiative black body cooling, which will basically lower the particle's temperature. And the last is the amount of heat used to basically vaporize the mass. So that also decreases the temperature. So because of that, we actually get very nice differential equation, which is our second differential equation. And the third one is about how mass is ablated, right? This is a standard ablation equation. Dm over dt is negative gamma rho v cube a over 2q, where lambda is the ratio of the kinetic energy that is used for vaporizing mass, right? And our q is just the heat of ablation. So now that we have a coupled system of differential equation, we can use this and run a simulation in MATLAB, solve it numerically, and then we will be able to analyze the results. So the constants that we have used are on the screen, and we also use the extra rule that the mass does not ablate until the temperature reaches 2500 Kelvin, which is actually the boiling point of silicate, right? And that actually does a pretty good job in the results that are in the upcoming slides.
So here we have some results for a 50 and a 200 micrometer particle that enters at 200 kilometers per second. So if we look down at the bottom right graph, it shows the temperature over time of each of the two particles. and they only are above the melting point temperature, so they're only ablating for about 3 seconds, which is pretty fast. And we also, on the top left, we see that the larger particle loses a larger proportion of its mass over the ablation period. We decided to look at how the size of the initial particle affects the proportion of mass lost. So for anything below 10 micrometers here, for both the 240 kilometer per second entry velocity, no mass was lost, so it never even got above the boiling temperature. And then after that initial radius, it started dropping off very quickly. And we see that the higher initial velocity, the smaller the particle can be, and it will still ablate. So the question that this problem poses is if we can look at some distribution of particles on the surface of the Earth and trace it back and see what the distribution was like before it entered the atmosphere. And ideally we could, because this model gives us some information about how size and speed of the particle results in its final mass, but we lose information along the way when we only look at a distribution of particle sizes or masses, because it tells us nothing about the entry speed of the particle. Here we have a plot of the final mass versus initial mass of some particles with two different entry velocities. And we see that for any given like final mass recorded, there are different and possible initial masses depending on what the entry velocity was. So this poses a bit of a problem if we want to just look at a distribution and go backwards and see what it was like on entry, because we just don't know what its velocity was. If we can just assume an entry velocity, so something like 14 kilometers per second, which is a commonly accepted value for that, then we can trace back essentially. So this upper plot is just a normal distribution of masses in some particles. It's not necessarily realistic, but it's just to illustrate what you could do. So with a distribution like this, and with a relationship between final mass and initial mass for a 14 kilometer per second velocity, we're able to trace back essentially. So we have this plot of entry distribution of particle masses. And so what this essentially does, it used the second plot from the previous slide to trace back the masses from the upper distribution. Now on the left side of the two plots, it's identical until you get to this little notch. And that's the point when the masses would have started to ablate, and then it starts to shift to the distribution to the right. That's about what you expect.
Yeah, so overall, we developed like two-part mathematical model to explore the fate of the cosmic dust particles as they enter the Earth's atmosphere, right? First of all, we looked at the trajectory and the deceleration of particles because of the drag force and the retardation due to it. And in the second part, we also talked about how heating, radiation, and ablation, all of these cause change in temperature, resulting in like the loss of mass, and then again change in velocity, and like there were lots of complications to that.
Our results show that particles that are much smaller and slower will burn up a little bit less, while faster, bigger ones will burn up more and lose more mass. And we also find that we can't exactly go backwards with our model, but if we assume some velocity distributions, then we can.
Okay, thank you.